Alright, so let us start today's class. So today we would be discussing another configuration. We had discussed earlier cascode and also current mirrors. So today we'll discuss another important configurations, so which is called differential amplifier stage. Now before starting differential amplifier stage, let us also discuss about this audio amplifier. So for example, here in this circuit, this part is representing a common emitter amplifier, which would be used as an audio amplifier to amplify the microphone output, right? So microphone, here I have a microphone over here. So microphone signal from the microphone will be amplified via this amplifier. Okay. Now in this audio amplifier, or simply common emitter configuration, we see VCC over here. Okay. So this is a DC supply. Okay. So VCC is a DC supply which can be obtained by AC to DC conversion, and for this AC to DC conversion one can use a diode rectifier. Okay. So diode and a capacitor. Okay. So this is a diode rectifier which converts AC to DC. Okay. So that is, input is AC over here, and at this end you get DC, which is being used as VCC here, okay, in this circuit. Now during the AC to DC conversion, it is possible that this DC, that is VCC, DC which we have created, so that DC may not be clean. Okay. So this DC voltage may not be clean, that is, it may contain ripples. Okay. So the DC obtained through AC to DC conversion via a diode rectifier, this may contain ripples. So the DC which we have obtained via conversion, so this DC, we would like this DC to be a straight line, constant, okay, DC voltage, but because of this conversion is not clean from AC to DC, so your DC is not clean and this DC contains ripples. Okay. So that means through VCC the ripple will be transferred to the output here, and also through the input the signal will be transferred at the output. So this amplifier will basically amplify the input signal from the microphone, and the output will contain both amplified signal. Okay. So the output will contain both amplified signal plus ripple. Okay. Now this ripple in the output, so this is heard as a humming noise in the audio output, right? So this is an audio output here, so audio output here. So this audio output will contain a humming noise, so user will perceive this, or user will note this humming, this ripple as a humming noise. Okay. So nobody likes a humming noise in the audio signal. Okay. So we want audio signal to be clean, we don't want humming noise in the audio signal. Okay. So now there are circuits which can reject or remove this ripple, so that my audio is free from humming noise. Okay. So this supply ripple rejection or humming noise rejection is possible by, for example, let us say this circuit. Okay. So this circuit contains two common emitter stages, right? So we have a common emitter stage here and here also. Okay. And let us assume that both these two transistors are identical. Q1 and Q2 are identical. RC1 and RC2, so both are same, equal. Okay. And input from microphone here is connected to Q1 at the base. Okay. So if I try to find out the output here, and in fact in this differential amplifier or differential stage, so this is my differential stage. Okay. So differential output is taken, right? So output is differential, that is the difference between the node potential at this point Vx and node potential at this point Vy. Okay. That is difference in the collector voltages of Q1 and Q2 are considered as an output here, or we say differential output. Okay. So when this input is applied to Q1 microphone, okay, so at Vx, that is the collector of Q1, we will see the amplified microphone signal plus ripple. Similarly, at this node Q2 of Q2 transistor, the output will contain ripple, or one can write Vx at the collector of Q1 is equal to the amplified version of the input signal. So input signal is V in. Okay. So V in multiplied by the gain of this stage plus the ripple. Okay. Similarly, the output of collector 2, that is Vy, so this will contain a ripple voltage Vr. Okay, since we have not connected any small signal here or microphone signal here, so the output will only contain the ripple. Okay. Now differential output means one has to take difference of Vx and Vy. Okay. So that is the final output, total V out would be equal to Vx minus Vy. Okay. So if I subtract Vy from Vx here, so I see that this ripple is cancelled and we are left with only this part. Okay. That is, now the output is free from ripple, or if it is used as an audio amplifier, then my audio is free from the humming noise. Now for sensing the difference between these two outputs, we need another amplifier which can take the difference between two nodes. Okay. And this amplifier would sense the difference between these two nodes. Okay. So another differential amplifier is required to sense the difference between these two output nodes. Now in this differential amplifier, it is important to remember that the output is of course differential, that is final output is the difference of the node potentials at Vx and Vy. The important thing to remember here is that differential input must also be applied. Okay. Differential input must also be applied because output is a differential output. So differential input must also be applied. Differential input here would mean that the input that is applied at Q1 and Q2. Okay. So this may be same in magnitude, but it should be different in phase. That is, it should be 180-degree out of phase at the inputs of Q1 and Q2. Okay. So I'll write here that the differential input here would mean that the magnitude of the input may be same, okay, or different, but phase should be different. Phase should be different or 180-degree out of phase the two inputs should be. Okay. That is, if I say this is V in 1 and this is V in 2, so V in 1 and V in 2 can be same in magnitude but should be 180 degree out of phase. If this condition is not met, differential input, then output of the differential amplifier will be 0. Okay. So how the output of this differential amplifier will be 0 if this condition is not met? So let us say that to Q1 and Q2 same input is applied. That is, V in is applied at both Q1 and Q2. So V in of this kind. So similarly V in 2 also of the same kind is applied here. So magnitude and phase both are same of the input signals. That is, V in 1 and V in 2 both are same signal, same magnitude, same phase. Now if I try to calculate the output Vx, okay, so since it's a common emitter configuration, so output will be out of phase with the input, okay, and magnitude will be more or less depending upon the gain of the circuit. Okay. So if the gain is AV of this stage, okay, then Vx, that is the output that is appearing here, so that will be out of phase. Okay, so if I have an input like this, or maybe let us say an input like this, so the output should be out of phase. Okay, so this is my V in and V out. Okay. So that is out of phase here means when the input is high, output should be 0. When the input is 0, the output is 1. Okay. Or high or low or high you can call, right? So input is high, the output is low. Okay. So this is out of phase. Okay. So at the output we will get an amplified version of this input, okay, and this will be out of phase. Okay. So for out of phase I'll have to 180 degree out of phase. Okay. So V out would be larger in magnitude depending upon gain AV and will be 180 degree out of phase with the input. Okay. So I get output of this kind here. Okay. Now this input to Q2 is also same, so output here will also be same. Okay. So now that means that at Vx and Vy we get these two outputs plus ripple. Okay. Plus ripple. Okay. So one can write Vx is, okay, node potential at Vx is gain multiplied by V in plus Vr. Similarly, Vy would be gain multiplied by V in, yeah, both V in are same, plus Vr, ripple coming from VCC. And the differential output Vx minus Vy then in this case would be 0. Okay. So if the input to the Q1 and Q2 transistors are not differential, so here in this case it is not differential. Okay. So both are same. So this will result into an output which is 0. Now let us take another case where the inputs are differential. Okay. So let us say Q1 we have plus V in and at Q2 we have minus V in input. So plus and minus here mean that minus here would mean that this input is out of phase with this. Okay. That is when let us say this is V in. So at Q1 if you apply this input, so Q2 you will have a out of phase input. Okay, right. So Q2, so let us say this input I apply at Q1 and this is at Q2. Okay, so I can call this as maybe V plus and this could be called as, or maybe this could be called as plus V in and this could be called as minus V in. So where minus here represents that this is out of phase with, I mean both are out of phase, right? So magnitudes may be same but phases are different. Okay, so differential inputs are applied to this differential amplifier, then let us see what could be the response. Okay, so that means that if the input to Q1 is this, then output would be out of phase with the input, and of course it will be amplified. Okay. Similarly, Q2, the output would be of this kind, right? So again, input and output, right? So I'll write here, these are the outputs of Q1 and Q2. So both output and input are out of phase with each other here also. They are out of phase with each other here also. And because it's a common emitter amplifier, so whatever you apply at the input, the output you will get an inverted input and with some magnification, okay, depending upon the gain of this circuit, okay, which is, let us say, AV. Okay. So one can find out again Vx and Vy. So Vx I can write as gain multiplied by input voltage plus ripple. Similarly, Vy I can write as gain multiplied by minus Vin, okay, plus Vr, which is ripple voltage. And the differential output, okay, V out. So one can write as Vx minus Vy is V out, which is, when I subtract this, this goes off and this becomes 2AV times Vin. Okay. That is the overall gain of this circuit with differential inputs is not overall gain, V out is 2 times AV times V in. Okay. So gain can also be written, I mean V out by V in is twice the gain of one common emitter stage. Okay. Now differential signals are again being explained over here, that is let us say we have a signal V in 1 and another signal V in 2. So here we can notice that both V in 1 and V in 2 are out of phase. That is, when V in 1 is high, okay, V in 2 is low. Okay. Similarly, when V in 2 is high, V in 1 is low. Okay. So this means it's a differential signal. Both are differential signals out of phase with each other. So they can be applied to my differential stage. Then now, so far till the previous lectures, we had studied a common emitter configuration, okay, and other configurations also we had studied, which had single-ended output, right? So single-ended output, and in the differential stage we have double-ended output, right? Output is at Q1 also and Q2, and the difference in the output is considered here. So it is, the output is a double-ended or differential signal output in response to the differential input signal, right? So input is also differential here, okay? Input at Q1 and Q2 both are out of phase here, so the outputs are also out of phase. Now one can make this circuit, the previous one, that is differential pair, this can be made more stable. Okay. So if I can attach a tail current source, right, that is, if I attach a tail current source over here, so I can make this circuit more stable. So we had some time back studied while reading this common emitter configuration that addition of a current source on the emitter side, so this actually sets up the collector current, okay, and now the collector current is set by the tail current, okay, so that the bias point is more stable, because bias point now not depends upon the VBE. Okay. So similarly, one can make this circuit also stable by attaching a tail current at the bottom here, for example. Okay. So for example, in this differential pair, a tail current source IEE is added here, connected on the emitter side. Okay. So now the collector currents, okay, that is this collector current IC1 and IC2. So both these collector currents are set by the tail current IEE. Okay. So this collector current IC1 and IC2, they are not now dependent on V in 1, and they do not change if my V in 1 changes. Okay. So this ensures that IC1 and IC2, okay, which are the collector currents, so they do not change. They do not change with change in V in, V in 1 or V in 2. Okay. So this is ensured by adding a tail current IE. So this makes this circuit more robust, okay, as the operating point is now more stable. Collector current is now fixed by this, and it does not depend upon V in 1 and V in 2. Okay. Now similar to a BJT based differential pair, so one can also think of using a MOSFET in designing these differential pairs. Okay. So again, in MOSFET based differential pair also one can add a tail source to set up the drain currents ID1 and ID2. Okay. Okay. So now let us also do some analysis on this circuit. Let us say that we want to find out the common mode response. So common mode here means that the input is common to both Q1 and Q2. Okay. So the same input is common to both Q1 and Q2, right? And let us assume that these two transistors are completely matched or identical. Okay. Q1, Q2 are identical transistors. Okay. And also let us say that the collector resistances, so they both are equal. RC1 is equal to RC2 is equal to RC. Okay. And since the inputs are same, so VBE, okay, so VBE1 would be equal to VBE2. Okay. So VBE1 and VBE2, so both would be equal. Okay. And if this is true, then the collector currents IC1 and IC2, okay, so they are also equal, okay, because this resistance is equal, transistors are identical, inputs are also same, so the collector currents are also same, which are equal to the tail current divided by 2. That is, half of the tail current flows in Q1 and half of the tail current flows in Q2. Now one can find out Vx and Vy. Okay. So Vx can be found, for example, from here, which would be equal to VCC minus drop across this, which is IC1 times RC1. Okay. So one can write Vx as VCC minus IC1 times RC1. Okay. And then one can say that IC1 is IE by 2. I can write IE by 2, and RC1 is equal to RC. Okay. So this gives me Vx is equal to this much. Similarly, Vy. Okay. So Vy is also same. So Vy and Vx both are equal because current through the transistors are equal and the resistances also are here equal. Okay. So that is why Vy, Vx both are equal, and since it's a common mode, that is input is same, so Vx minus Vy, that is also the output of this differential state, so that will be equal to 0 in this case. Now we had commented that because of this tail current, my circuit is more stable as the IC1 and IC2, so they are fixed by this tail current. Okay. And my collector currents now, they do not depend upon the input. Okay. So In fact, we have a limitation on this input. Okay. So we understand that since the collector currents are set by this tail current, so that would mean that even if VCM goes up, the collector current should not change. Right? IC1 and IC2 do not change. Okay. Okay. So that means VCM can increase and it will have no effect on the two collector currents. Okay. But there is a limit for this VCM to change, right? So that is the upper limit of VCM, that is up to what point VCM, that is input to these two transistors, can go up. So that can be uh, you know found from here itself. Okay. So we find that Vx is this much. Okay. So we find that Vx is VCC minus RC times IEE by 2. Okay. And imagine if at the input here VCM is also this much. Okay. So let us say VCM, that is this input, so this is also same. Okay. IE by 2. Okay. So this is fine, no issues. But if this input, it increases above this value. Okay. So if this input increases above this value, so that would mean that base is now at a larger potential than the collector. Okay. So base is now more positive than the collector. Okay. So this would make my collector base junction forward biased. Okay. So when collector base junction is forward biased, so then this transistor Q1 enters saturation. Okay. And we want BJT to always operate in active region. So that is, the collector base junction should be reverse biased always. But in this case, if my input goes beyond Vx, which is this value, then my collector base junction becomes forward bias and my transistor Q1 or maybe Q2 also, they both enter saturation. Okay. So which sets actually the limit, upper limit on VCM, that is the common mode signal. So common mode signal should not go beyond this point, that is Vx or Vy, which is VCC minus RC times IE by 2. Okay. So the common mode signal can change, increase, no problem. IC1 and IC2 will not change. Okay. So these two signals can change, but there is a limit that they can increase only up to Vx or Vy, okay, which is equal to VCC minus RCIE by 2. Now let us take some examples. So here let us say that V in 1 is plus 2 and V in 2 is plus 1 volt. Okay. And RC, they both are same. Okay. And we have a tail current also here. Okay. Now since the base of Q1 is at a higher potential, okay, so the current drawn by the collector will also be larger than the current drawn by the transistor 2. Okay. Since base of Q1 is at a higher potential than the base of Q2, so current drawn by Q1, which is IC1, will be larger than the current drawn by Q2. Okay. So which would also mean that Vx would be smaller than Vy. Okay. So since IC1 is greater than IC2, okay, because V in 1 is greater than V in 2. Okay. So therefore IC1 should be greater than IC2, and therefore Vx, that is collector, the output at the collector should be smaller than the output at collector Y. Okay. So the differential output can be taken across this Vy and Vx, okay, as Vy minus Vx. So this is my V out, okay, because Vy is at higher potential than Vx. So the total differential output is V out is Vy minus Vx. Okay. Now in this case, if we assume that VBE 1, that is VBE of this Q1 is 0.8 volts, then VP here, okay, so this VP would be equal to then 2 minus 0.8, which is equal to 1.2 volts, right? So VP here is 1.2 volts then, okay. Now when VP is 1.2 volts and in transistor 2 we see V in 2 at the base is 1 volts. Here VBE is minus 0.2 volts. Okay, so VBE is minus 0.2 volts. Okay, so this transistor will be off. Okay, so this is on, but this transistor will be off. So when this transistor is off, so that means the entire tail current flows through transistor 1. Okay, because current through this transistor Q2 is 0. So entire tail current will flow through the transistor 1. Okay. So I can write IC1 as IEE and IC2 as 0. So Vx could be written as VCC minus RC times IEE, and Vy, since this is off, so Vy here would be equal to VCC. Okay. Now let us take another case. Okay. So this time the input of transistor 2 is larger than the input of transistor 1. Okay. So V in 2 is greater than V in 1 this time. Okay. So this would mean that IC2 will be larger than IC1. Okay. So V in 2 is greater, so IC2 will be larger than IC1. Okay. And this would mean that Vx, that is this potential, so this Vx will be larger than Vy in this case. Okay. So one can take a differential output as Vx minus Vy. Okay, here. Now again one can assume here that the base to emitter voltage of Q2 is 0.8 volts, so Vp here now again is 1.2 volts. Okay. Now this is at 1 volt gate, sorry, base voltage, so that means this transistor will be off and this is already on. Okay. So when this is off, so that means IC1 would be 0 and the entire tail current will flow through the collector of transistor Q2. So IC2 I can write as IEE. Okay. So IC2, that is the entire tail current flows through the collector of transistor 2. IC1 is 0, so Vy can be written VCC minus RC times IE, and since Q1 is off I can write Vx as VCC. Okay. Okay. Now from these two circuits, that is this differential response 1 and differential response 2, okay, I can now use these two responses to plot the IV characteristics of differential pair. Okay. So IV characteristics of differential pair can be plotted by seeing or looking at the response 1 and response 2 that we have just now seen. Okay. So in the IV characteristics we are interested in IC1 and IC2 collector currents, and for voltage V, instead of saying V in 1 and V in 2 separately, we would plot V in 1 minus V in 2 on the x-axis, okay, and on the y-axis the two currents IC1 and IC2. Okay. Now we had seen from these two circuits here, that is these two responses, okay, that when V in 2 was greater than V in 1, then IC2 was greater than IC1. Okay. Or one can say that when V in 2 increases, IC2 increases and IC1 decreases. Okay. So I can write here that when V in 2 increases further, okay, then this implies that IC2 also increases and IC1 decreases. Or I can write here that, yeah, so this is what I can find here. Okay. Or I can also write from here that this response, V in 1 was greater, so IC1 was greater. Or I can write then that when V in 1 increases, IC1 increases and IC2 decreases. Okay, so I can write here that when V in 1 increases, so this would mean IC1 increases and IC2 decreases. Okay, so I can plot the IV characteristics by knowing these two things. Okay, that is, this is one, and the other one, that is this one. So let us plot the IV characteristics knowing these two things. Okay. So I'll write the same thing here also. That is, let us take from here. V in 2, IC2, IC1. Okay. So when V in 2 increases, IC2 increases, we had written, and IC1 decreases. Okay. And sorry, V in 2 here, and then when V in 1 increases, IC1 increases and IC2 decreases. Okay. And on the x-axis, since we are plotting V in 1 minus V in 2, so this is the point where V in 1 and V in 2 both are equal. Okay. So this is the point where V in 1 and V in 2 both are equal. Okay. Or V in 1 minus V in 2 is 0. Okay. That is, both the transistors are being fed with the same input, magnitude is same. Okay. So this would mean that the currents through the two transistors will also be same, and the currents IC1 and IC2 are equal to IEE by 2 at this point. Okay. Then V in 1 minus V in 2 is increasing, so that means V in 1 is increasing. Okay. So if I look from this point towards right, so this means V in 1 minus V in 2 is increasing, so that means V in 1 is increasing. Okay. So that means IC1 should increase, so IC1 is increasing. Okay. This is IC1 here, increasing, and oh sorry, this should be down here. IC1 is increasing, and from this point IC2, that is this current, so this is decreasing, right? So which is true here from this. Okay. Similarly, if I move towards the left from 0, okay, so this would mean that V in 2 is increasing. Okay. V in 1 minus V in 2 ratio is becoming negative, so that means V in 2 is increasing here in this part. Okay. So here V in 1 was increasing, so in this part V in 2 is increasing, so V in 2 increases, then IC2 increases, IC1 decreases. Okay. So IC2, that is this curve, this is increasing, and IC1, that is this curve, this is decreasing. Okay. Now when we had also said that when IC2 increases, okay, so drop across the Q2, so that increases, so Vy should reduce in this case. Okay. Similarly, when IC1 increases, then drop across the transistor 1, so that should decrease. Okay. Okay. So we will again now plot here the differential input on x-axis versus the outputs Vx1 and Vx2. Okay. And this is again the point where V in 1 is equal to V in 2, okay, which is, and the difference is V in 1 minus V in 2, which is 0. Okay. So at this point, V in 1 minus V in 2, that is V in is equal to V in 2. So we had written that both Vx and Vy, so they are equal, which is equal to Vcc minus Rc times IEE by 2. Okay. So I'll take you back here. So we had written here that Vx is Vy is equal to Vcc minus Rc times IEE by 2. Okay. So that is, this point is clear now. When Vin is Vn2, then both outputs are same, which is Vcc minus Rc times IEE by 2. Okay. Okay. Then when Vin1 increases, okay, Vin1 is increasing, so this term is increasing. So here the differential input is decreasing, so that means Vin2 is increasing. So when Vin1 is increasing, so we see Vx should come down. Okay. So when Vin1 is increasing, Vx1, so this is coming down, and Vy2, so this should increase here. Similarly, Vx should increase here. Okay. Now when we move on to Vin2, when Vin2 is increasing on the left side, that is this part, so Vy should decrease, that is Vy2 is decreasing, okay, and Vx1 or Vx, so this is increasing, so Vx is increasing. Okay. So that way one can plot the IV characteristics. Okay. So both one can plot or one can understand the IV characteristics from the response of the differential stage. Okay. So one can find out the IV characteristics. Now one can also perform the small signal analysis. So let us say that at the inputs of these two transistors, okay, there is a differential change in the input, that is the input at transistor Q1, this rises by delta V, and input at transistor Q2, it falls by the same amount delta V. Okay. So input to Q1 and Q2, so they rise, okay, here it is rising, and they fall, here it is falling by the same amount delta V. Okay. Now when the input is rising over here, so that means IC1, so this should also rise. Okay. And when the input is uh, falling here, so that means that IC2 here, okay, so this should come down. Okay. That is, this IC1 here, it should increase, and IC2 should decrease here. Okay. And this reduction or increase in IC1 and IC2, this should also be by the same amount. So let us say that if IC1 is increasing by delta I, okay, then IC2 should reduce by the same amount delta I. Okay. So that is, one can write IC1 in response to a small uh, rise in input delta V as IE by 2 plus delta I, that is, this collector current changes by delta I amount. Similarly, the collector current at 2, so this will fall down by the same amount delta I, that is, it will be equal to IE by 2 minus delta I. Okay. So this is important to understand here, that the rise and fall at the input, if they are of same magnitude, then the collector currents will also change by the same magnitude, that is, rise and fall would be of the same magnitude, that is delta I. Now if this is true, that is, the collector current is changing by the same amount in response to the rise and fall at the input by the same amount delta V. So for this to be true, this node potential Vp, so this should be fixed. Okay. So for the previous condition to be true, that is, the collector current is changing by the same amount in response to the change in input by the same amount. So for this condition to be true, I need to ensure that Vp, that is this node potential, is fixed. Okay, so this does not changes. That is, change in Vp should be 0. Okay, this node should be fixed, or this node should be, can be treated as AC ground. So this is important to note here, that this VP node, this P node, can be treated as a AC ground, okay, in small signal analysis, okay, if we are considering this condition. Now the GM of the transistors can also be calculated. Since both are identical, GM should be same. So GM based on the changes in the collector current and changes in the input voltage can be calculated. So GM can be written as delta IC 1 by delta V. Okay. Similarly, the GM of other transistor, so which is also same, so that can be written as delta IC2 by minus delta V. Okay. So because at transistor 2 Q2, the input is falling by the same amount delta V. Okay. So one can write delta IC1 is GM times delta V and delta IC2 is minus GM times delta V, and this node P can be viewed as AC ground in this situation. Okay. Now one can also find out the small signal differential gain of this circuit. So for finding out the small signal differential gain, one has to short all the independent currents, independent sources to ground. So that is, this VCC will be shorted to ground. Okay. Similarly, this tail current source, so this will also be shorted to ground here, or I mean this will be open here and this will be shorted to ground. Okay. So one can find out the collector current or change in collector current delta IC and delta IC2, okay, in response to change in the input voltages. Okay. So one can draw the small signal model circuit. So for example, for this half, that is one half for only Q1 transistor, a small signal model circuit is shown over here. Okay. So which contains V in, okay, which is delta V. Okay. Then we have R pi and V pi or V in or delta V dropping across this. Then GM V pi, or in this case it should be GM delta V. Then collector resistor RC. Okay. And at this node one can find Vx. Okay. Now for this circuit one can write delta IC as GM times delta V. Right, so delta IC 1 as GM times delta V. Okay. So delta IC1 can be written as GM times delta V, and delta Vx, that is this node potential delta Vx. Right, so this can be found by simply multiplying this current GM delta V multiplied by RC. Okay, and this should be negative since it's a common emitter configuration's output. So one can write Vx as minus GM times delta VRC. Right, so Vx is minus GM delta V times RC. Okay. Similarly, one can find out by drawing the small signal circuit of Q2, one can write delta I2 as GM times delta V, but this time delta V is minus delta V over here. So one can write IC2 as GM times minus delta V, and Vy one can write as minus GM RC, not minus GM RC, minus GM delta V times RC. So delta V is negative, so this will become plus GM delta V RC. Okay. And then one can find out Vx minus Vy. Okay. And if I divide it by, I mean this is output, Vx minus Vy, and if I divide by input, which is delta V here and delta V here, so that is 2 delta V. Okay. So this will give me gain, which is mentioned over here. So Vx minus Vy, that is delta Vx minus delta Vy. Okay, that is GM delta V minus GM delta V RC minus GM delta V RC. So this gives me 2 minus 2 GM delta V RC divided by this 2 delta V. Okay, and which is equal to minus GM RC. So total gain of the differential pair is minus GM RC. Okay. Now if you remember, the gain of common emitter configuration with single ended output. So this is also minus GMRC. Okay? That is the gain of this half part, half circuit, which is common emitter configuration, single ended output. Okay? So the gain of this also is minus GMRC. So that means the gain of differential amplifier, okay, the gain of differential amplifier and common emitter stage. So both are same. So gain of differential amplifier and common emitter stage. So both are same, which is equal to minus GMRC. Okay. So then what is the difference between these two configurations? The difference lies in the power dissipation, which is actually doubled in the differential pair. Okay, because you have two transistors, both the transistors are drawing power from VCC in terms of current drawn from VCC. So VCC is my power supply. So power dissipation here is doubled in comparison to a common emitter stage. Now similar to the small signal analysis, one can also do the large signal analysis, that is DC analysis, right? DC or large signal analysis can be done. Okay. So for DC analysis, one can obtain these two equations, IC1 and IC2. Okay. So how to obtain these two equations? Let us assume that IC1 is flowing through Q1 and through Q2 it is IC2. Vout1 is present at the output of Q1 collector of Q2 we have Vout2. Okay. Now this collector current equation, that is IC1, can be written by using the collector current for BJT. So collector current for BJT is Is e to the power VBE by VT. So through this I can write IC1. So IC1 is that means Is times e to the power V in 1 minus Vp. Yeah, VBE here is, this is base and this is emitter over here, and Vp is here. So V in 1 minus Vp by Vt. Okay. Similarly, IC2 can be written, which would be Is e to the power VBE, that is V in 2 minus Vp by Vt. Okay. And one can also write this relation, IC1 plus IC2 is IEE. Right. So this IEE is, I can write IC1 plus IC2. Okay. Provided V in 1 and V in 2 both are same in magnitude, and these two transistors are identical. Okay. Resistances are already equal. So IC1 is IE is IC1 plus IC2 I can write. Okay. And IC1 and IC2 we have already obtained over here. So put these in this equation. So I get IEE as this much. Okay. Yeah, so IEE as this much I get, and from here then I can find out IC1. Okay. Just a second. Okay. Yeah, so IEE we have this much, Is times, okay, V in 1 minus Vp by Vt plus V in 2 minus Vp by Vt. Okay. So from here I can find out Is. Okay, so Is is IEE by this term. Okay, and this Is I can put over here to find out IC1, or the same Is I can put here to find out IC2. Okay. So let us put Is as IEE by this term in IC1 equation. Okay. So I get IC1 is now IEE times e to the power V in 1 minus Vp by Vt divided by V in 1 e to the power V in 1 minus Vp by Vt plus e to the power V in 2 minus Vp by Vt. Okay. Now in this equation, now I take V in e to the power V in 2 minus Vp by Vt common outside the bracket. Okay. So if I do that, I get this relation, and then finally this relation can further be simplified to this relation over here, which is similar to this equation. written over here, IC1. Okay. So both these two equations are same. Okay. So the collector current, that is IC1 and IC2, both can be obtained. Okay. So and these two depends upon the value of V in 1 and V in 2. So if V in 1 and V in 2 are same, then one can say that IC1 is IC2. Okay. But if V in 1 and V in 2 are different, okay, so for example V in 1 is larger, then IC1 should be larger than IC2. By how much amount? So that can be calculated by these two relations. Okay. Now similarly, the IO characteristics or DC input output characteristics or large signal IO characteristics can be drawn. Okay. So similar to the IO characteristics we had seen for a small signal, the large signal IO characteristics can also be drawn. Okay. So they are also similar. Okay. Because we understand that when V in 1 increases, IC1 increases, IC2 decreases. Right. So V in 1 is increasing when I'm moving from 0 to this point towards right. So when V in 1 is increasing, so IC1 is increasing, it reaches up to IE. Similarly, IC2 should decrease, and when V in 2 is increasing, so here V in 2 is increasing, here V in 1 is increasing. Okay, so when V in 2 increases, IC2 increases, and at that time IC1 should decrease. Okay. And by what amount these should decrease? So that can be calculated from these two relations, IC1 and IC2. So that way one can draw the IV characteristics and also V out and V out 1 and V out 2 versus V in 1 minus V 2. So all these characteristics can be plotted. Okay. Now let us also discuss the small signal model. In fact, the half part we had already discussed for one transistor. So let us say that we want to draw the small signal model circuit for this complete differential pair. Okay. So one can draw it by considering VCC is shorted to ground and this current source is open. Okay. So one can draw it. So we have V in 1 here, R pi 1, okay. Then GM1, V pi 1, RC. Okay. One can draw this down also here. Okay. Similarly, this can be drawn down here. Okay. Then we have R pi 2, V in 2. Okay. Now let us also introduce the concept of half circuits here. Okay. So because this concept of this half circuit, so through this I can simplify any complex looking differential pair circuit, and then the gain and other things can be calculated very easily. So half circuit means simply dividing this circuit into two halves. Okay. So when I divide this circuit into two halves, so that means in one half I'll have RC. For example, Q1 will contain RC, V in 1, and this tail current source. So this will be divided. That is, I'll have IEE by 2 here. Okay, IEE by 2. Okay, in both these circuits. Okay. So for example here I can draw the half circuit considering VP is a virtual ground. Okay, that is, this node is virtual ground. I can draw the half circuit, that is the two common emitter configurations separately. Okay. And for the two common emitter configurations, the small signal model here are drawn. So this is one half pair and this is another half pair. Okay. And we have considered VP is grounded, that is emitter is grounded of both the transistors in the small signal model. Okay. So we can treat this differential pair as two common emitter half circuits. Okay. So differential pair can be treated as common emitter half circuits. Common emitter half circuits. And the gain of this pair, so this is minus GMRC. and of this pair also it is minus GMRC, which is the total gain of this circuit, differential pair. Okay. So total gain of the differential pair is also minus GMRC. Okay. That is the gain of this differential pair is equal to the gain of a common emitter stage with single-ended output, right? Single-ended output. So using this concept, we can simplify the complex looking differential pairs, and then we can find out the gain of any complex looking circuit. Okay. So we'll see some examples also. So for example, we want to find out the differential gain of this circuit. Okay. So the differential gain can be found. So in fact that gain is V out by V in, right? V out by V in we want to find. So V out here is V out 1 minus V out 2. Let us say this is V out 1 and this is V out 2 divided by V in, that is differential input V in 1 minus V in 2. So this is the gain of this differential pair. Okay. And we said that if I can divide this circuit into two halves or half circuit, so this is one half circuit, okay, and this is other half circuit. Okay. So I can find out the gain of this half, which will be equal to the gain of this entire differential pair, and the gain of this circuit is considering no RC. Okay. So RC is nothing here, 0. So we have only RO1 and RO2 associated. Okay. And since I said that these two transistors are identical, so RO1 and RO2 should also be equal, which will be equal to, let us say, R0. Okay. So the gain of this circuit would be minus GM times RO. Okay. For both these two circuits, right? Minus GM times RO, and for this circuit also minus GM times RO, considering RO1 is equal to RO2. Okay. So the gain of the half circuits is minus GM R0, and the gain of this full circuit, okay, so this is also equal to minus GM R0, because there is no RC over here. Okay. Now let us consider this example. Okay. So again, for finding out the gain, one can divide this circuit into a half circuit. So for example, a half circuit is drawn over here. So this half circuit now contains R1. I mean, you divide it from here. So this R1. Okay. So we have R1 over here, and this is AC ground. Okay. So this circuit is simplified as this circuit. Okay. Q3 and Q1 in one half circuit, Q4 and Q2 in another half. Okay. So I can find out the gain of this circuit, okay, so by knowing that the impedance looking into Q3 is RO3, okay, and impedance looking into the collector of Q1, so this is RO1, or one can say RO1 in between the drain and source. Okay. So that is all these resistances RO3, RO1 and R1 are in parallel. So one can write the gain of this circuit as minus GM times RO1 parallel to RO3 parallel to R1. Okay. Okay. Now the gain of this part, this half circuit, is equal to the gain of this complete differential pair. Okay. Because we have already said that the gain is minus GMRC for a differential pair, and for one half pair also it is minus GMRC. So in absence of RC and presence of R0, okay, lambda is here not 0. Okay. So one can write gain as minus GM times all these resistances in parallel. Now another example let us take. So we want to find out the gain of this complex looking circuit. Okay. So again, to simplify this, we'll draw the half circuit. Okay. So for drawing the half circuit, that is the half part will contain R1. Let us say this part we draw Q3, Q1, okay, and R1 connected to node X, okay, which is connected to ground here in the small signal model. Okay. So in the small signal model, this is grounded, okay, and the gain of this circuit, if I can find, then that will be equal to the gain of this entire differential pair. Okay. So for finding out the gain of this circuit, we'll again see that the collector current, sorry, the collector, the impedance looking into the collector of Q3 is, I'll write RO3, okay, and the impedance looking into the collector of Q1, so this is RO1, okay, or RO1 is in between drain and source, okay, and right, and RO3 is also between drain and source, okay. So this RO3 is also between drain and source, right. So all resistances are in parallel, so one can write the gain as minus GM times RO1 parallel to RO3 parallel to R1. So the gain of this half circuit is this much, which is also the gain of this full circuit. So for this also the gain is same, RO1 parallel to RO3 parallel to R1. Okay. Considering that these two transistors are identical. Okay. Now similarly, let us take another example where we have to find out the gain of this circuit. So again you will divide this into two halves. Okay. So let us say Q1 half we want to draw. So it will contain a Q1 transistor RC RE. Okay. So for this circuit one can find out the gain. Let us say that lambda is 0 for this circuit. Okay. So one can write the gain as, so this is common emitter configuration with emitter resistance. So we had found the gain of this circuit as minus GMRC by 1 plus GMRE some time back. Okay. So while discussing common emitter configuration with emitter degeneration resistance, we had found the gain of this circuit as this much. So the gain of this circuit remains this, which is also equal to this. Okay. So this is the gain of the half circuit, which is also the gain of the full circuit, differential pair. Okay. Okay. So the gain of this circuit is this. I mean it is equal to the gain of the half circuit. Similarly, let us consider last example for the day. Last slide also, I hope. Yeah. Maybe let us see. Yeah. So we'll end here itself. Let us take another example over here where we want to find out the gain of this circuit, right? So we again divide this circuit into two halves. So this time this RE will be distributed equally in these two halves. That is, RE will be equal to RE by 2 for this circuit. And the gain can again be written by the same previous circuit. I mean both are same except RE is RE by 2 here. So the gain will be simply minus GMRC by 1 plus GMRE, common emitter amplifier configuration with emitter degeneration resistance. So RE is simply RE by 2 over here. So I'll say 1 plus GMRE by 2. Okay. So which is the gain of this half circuit. Okay. And this gain is equal to the gain of this complete circuit, complete differential pair, right? So both gains are same, right? So with this I'll end today's lecture. Okay. So we'll meet in the next lecture then.